one of the very first things, or one of the later things that we sort of enforced, or not enforced necessarily, but stated when we were dealing with sort of this section 2.2, is this idea of completeness, that any arbitrary wave function, big psi, can sort of be decomposed into this infinite sum of stationary states, psi naught, phi naught, psi 1, phi 1, etc., with each state having some coefficient c in front of it. So the way that we interpreted this was that these c coefficients were actually probabilities. So big psi is apparently a superposition of all of these stationary states, and apparently, if we observe big psi, what we get is the probability, C naught, C1, C2, etc., gives us the probability of finding our state in one of these stationary states. So if we observed our system, big psi, apparently there is a magnitude C naught squared chance to find our particle in the n equals 0 stationary state, a magnitude C1 squared chance to find our particle in the n equals 1 stationary state, and so on and so on. And one of the problems that we sort of encountered was that this isn't necessarily something that we can very easily prove, especially completeness. Completeness can be very difficult to prove mathematically for more complicated systems, and this is also something that we can't necessarily prove, that C naught, C1, etc., is apparently sort of this probability of finding our wave function at these points. Sort of earlier on, we made the argument that observations sort of collapse our wave function and force it to take on some specific value given some physically observable quantity. However, that was more of just sort of introducing things, and it isn't necessarily a proof for this. We will not prove this for now. Later on, once we have more knowledge with quantum mechanics, we might. But for now, we are also sort of taking this at face value. However, what we can do is we can prove some of the consequences of this being true. And sort of one of the things that this requires, because of the fact that magnitude Cn squared is this probability, is that all of these resulting probabilities must therefore equal 1. And the goal of example 2.3 is to sort of verify this consequence. Now, this isn't necessarily a proof. However, we are simply just observing and confirming one of the many different consequences of Cn sort of being this probability. So we're going to do this for two things. In part 1, we're going to start with sort of the expression that we had in example 2.2, and we're going to verify that that one equals 1 for all of the Cn terms. And then after that, in part 2, we're going to sort of prove this more generally for any wave function. So let's start right off with the Cn expression obtained from problem or example 2.2. So let's write this in red. In example 2.2, we sort of got this expression for Cn, which is that Cn equals one of two formulas. It either equals 0 or it equals 8 times the square root of 15 divided by n pi cubed. And this is when n is even, so equals 2, 4, 6. There should be a 0 at the front, but it doesn't really matter. And then the bottom is for the odd case, n equals 1, 3, 5, and so on and so on and so on. So, evidently, we want to prove that adding all of these odd ends together, because we can ignore the even ends since it just equals 0 anyway, apparently this has to equal 1. So, let's sort of write this out fully. So, the summation from n equals 1 to infinity of the magnitude of Cn squared is equal to, and we can take all the constants at the front and sort of just square them like normal. So 8 times square root of 15 divided by pi cubed. And this whole thing is squared, and we can remove the magnitude signs because there's no complex numbers here. And then we're going to take our summation as normal, so n, and actually in this case, our summation is going to be n is only odd, n equals 1, 3, 5, etc., etc., etc. all the way up to infinity of 1 over, and here we have n cubed, so we're squaring it, so it's going to become n to the 6th. And hopefully you still remember how to sort of resolve series. This series ends up converging to pi to the power of 6th over 960. And this does, in fact, sort of cancel with that to become exactly 1. So this is apparently true for sort of the specific example we introduced in example 2.2. The next goal is to prove this more generally. So if you want to prove this more generally, one thing that we can do to sort of do this is we can sort of start off with our normalization condition, because where our goal is to prove that this is true. So we need to get this 1 from our equation somewhere, and one place where we can go to get this is from the normalization equation. So we know that 1 has to equal the integral from magnitude psi squared dx. And in fact, I can go one step further, and I can say I'm specifically working with magnitude psi of x comma 0. I don't necessarily have to do this. If we worked with magnitude psi of x comma t and included sort of the phi expressions, we can do the exact same thing. However, it isn't necessarily required because all of the phi terms cancel out under a magnitude squared sign anyway. So we can just work with sort of this big psi of x comma t equals 0. From here, we use the completeness theorem. So this is equal to the integral of the summation of, let's use m here, of cm psi m star, or little psi m star, multiplied by sort of the summation, but using n index this time, of cn times psi n star, or not psi n star, just psi n itself. And from here, the first thing that we can sort of do is simplify this a little bit, make it look a little bit nicer. And what we can do, this is in terms of x purely. The coefficients cm and cn both don't have to do with these, with the integral, so we can move these summations out. It's going to be summation of m times summation of n, cm cn times integral psi m star times psi n dx. And from here, we just have to take advantage of the fact that stationary states are orthonormal, apologies, because remember, we sort of showed earlier on that this expression is equal to the Dirac delta, or Kronecker delta, of mn. Because if m does not equal n exactly, then this expression just cancels out to 0. So, therefore, what we can say is that this equals sort of the magnitude, or the summation of the magnitude of cn squared, because m necessarily has to equal n, or otherwise all of these terms equal 0. And just like that, we are sort of back at our original proof, because this we originally postulated has to equal 1.